Okay, well, we're going to get started with Dr. Steve Heymsfield.
Thanks very much. You're going to see some of the same slides again as you have before, but should be okay. One of the fascinating things over the past century is the epidemiological transition. I don't know how many of you are familiar with it, but with the reduction in deaths due to infectious diseases at the beginning of the last century, there's been a rise in the prevalence of chronic diseases, including a rise in the incidence of cancer. And the population has also been aging, and the population's become more obese. The confluence of all of those things together really is driving the interest in not only cancer, but sarcopenia and obesity as well. All of these things come together at some level. Uh-oh. Okay. All right, that's a good start. Okay. So at the beginning of the last century, the phenomenon of cachexia was very well established. Diseases like tuberculosis, inflammatory diseases, were highly studied and associated with cachexia and wasting diseases. And in the 1950s and 60s, there was a very large body of work on cachexia syndromes like pulmonary cachexia, cardiac cachexia, AIDS more recently. And so the study of cachexia is very well established, and people who are cachectic, as you know, not only have muscle wasting, but they have a number of other biological phenomena associated with inflammatory state. For example, they tend to have low-grade fevers. There's anorexia. Often you find organomegaly, not always, but these diseases have been fairly well phenotyped over the years. On the other hand, if you look at malnutrition, this is the Minnesota experiment, experimental protein-calorie malnutrition, and related the famines that occur in natural settings, protein-energy malnutrition, like marasmus. The phenotype's almost identical in appearance on the surface, but these are very different states. And with protein-energy malnutrition, people are hypometabolic. They have atrophy of both fat and muscle. Organs are often reduced in mass, and their mechanisms for intake of food, leptin and the whole circuitry, neural circuitry, are activated. These people are usually very hungry, as opposed to cachexia, is often anorexia. So even on the surface, these conditions look similar. They're quite different. Then in the 1980s, one of my friends, Erwin Rosenberg, who's the head of the USDA in Boston, he was very interested in diseases such as osteopenia, loss of bone mass with age. And at his center, probably many of you know Dr. Rosenberg, they were also very interested in whether or not you could reverse the age-related loss in muscle mass, and he coined the term sarcopenia. Now, sarcopenia, again, looks phenotypically very similar to those other conditions, but the biology, as you know and have heard, is very, very different. It's a very different condition. And then frailty, another syndrome that sort of comes on the radar, is also a state that people have studied very extensively and overlaps to some extent with these conditions. And then finally, most recently, obesity. The interest in obesity and the combination with sarcopenia is very profound. It first began with the so-called double burden in countries where there's a high prevalence of both malnutrition and obesity. These two things can be confluent in the same people. You can be both obese and protein energy malnourished in the sense that you have muscle loss. And so obesity sarcopenia or sarcopenic obesity has come on the radar. So all of these conditions share in common one thing. They all have loss in muscle mass, but yet their sort of biological underpinnings are very, very, very different. So that's, I'm going to present very briefly just sort of some of the definitions people have used, and you've heard a lot of this today, but I'll go through them quickly, and then more importantly, I'll give a prelude to the presentations that will come and talk specifically about the use of body composition and phenotyping these conditions. Well, as you've heard, there's this sarcopenic spectrum. Basically, sarcopenia is the skeletal muscle loss with aging, both mass and function. And that in turn leads to, of course, weakness and morbidity. That's the paradigm we're in. And often people refer to the loss of muscle mass as myopenia. And as we heard earlier from Tammy, myosteatosis can be a phenomenon, the change in composition of muscle, not just the mass, but the composition of muscle is an important issue. And the weakness component is often referred to as dynapenia. There are a lot of different terms floating around in this literature. And then we get the relationship with adipose tissue and the effects of adipose tissue on metabolic functions and ultimately morbidity. And so there's these combination of factors that ultimately lead both to weakness and morbidity, and then sarcopenic obesity at the other end of the spectrum, and then cachexia and frailty. These phenomena all are confluent, and their definitions aren't always clear, nor are the separation between them clear, and they can occur in the same people. With respect to sarcopenia, as you've heard earlier, there's primary sarcopenia. According to some people, that's the age-related effect. Secondary can be related to cachexia, and so there's some cloudiness in a sense over how these phenomena are defined, but some people refer to cachexia and secondary sarcopenia as similar. And then there's the stages of sarcopenia. You heard earlier, pre-sarcopenia, sarcopenia, and severe sarcopenia. Now, this point's been made several times today, but this is just the age-related change in muscle function and muscle mass, and several people have made the very important point. This just shows that as people age, if you look at the relationship between mass and function, either by knee torque, hand grip, or muscle power, you see a discordance between them. You see a much larger reduction in function than you do in mass. And so mass and function are not equivalent. They are different, and with aging, for sure, you see a difference between the two. And also in the short term, you can see a big increase in function with training with relatively little change in mass. So mass and function are not equivalent. These are just some of the definitions people have used for sarcopenia, and we've seen this slide earlier today. But all of these definitions, and there's several, this is the European Working Group on Sarcopenia in older people, and they all have the same basic structure of looking at function as physical performance, strength, and mass. Those three things, performance, strength, and mass, are used in these paradigms for ferreting it out who is and who isn't sarcopenic. And these are just some of the numbers that are used. This is the foundation for the NIH paradigm, very similar relationship between grip strength and mass, diagnosing in this algorithm for diagnosing sarcopenia. Now, sarcopenic obesity, the definitions are all over the map. Carla Prado is going to speak tomorrow, gave me some guidance on this, but basically they all share in common the measurement of muscle mass and some other measure of body adiposity, such as weight, BMI, fat mass, or fat mass index. So the phenotyping of sarcopenic obesity is still a little confusing, but nevertheless, the idea is that you can have both too little muscle and too much fat in the same person, and that has certain morbidity and mortality consequences. And lastly, we heard a little bit of this earlier, and I do lament the loss of Ken Fearon, who was a real pioneer in this area. But he and others put out the definition of cachexia as a multifactorial syndrome characterized by an ongoing loss of skeletal muscle mass with or without loss of fat. And as I mentioned, with cachexia and wasting diseases, you can have loss in muscle independent of fat mass. And with cancer, very interesting work done maybe 75 years ago, concept advanced the nitrogen trap hypothesis, and we heard this earlier today, that the growing cancer the growing malignancy can trap protein in it, and that protein comes from muscle, which has an expendable source of protein. You can live without the protein in your muscle, but you can't live well without the protein in your liver that's making inflammatory mediators and so on. So that idea is that you can still have too much fat, but specifically losing muscle, and that the cachexia syndromes are not often easily reversed with conventional nutritional support, and they're associated with functional impairment. So that's cachexia. And this is, you saw this earlier, but the diagnostic criteria for cachexia according to this Fearon paradigm is that basically loss in body weight, change in BMI, or loss in muscle mass over time into different categories can lead you into the pre-cachexia, cachexia, and refractory cachexia. And this is just another definition of cachexia, but basically all surrounding the idea of weight loss and skeletal muscle loss. Now, turning to the body composition side of it, when we think of body composition, we can put it into these levels of going all the way from elements. We're made out of elements, of course. The molecular level, such as lipid, water, protein, and so on. The cellular level, such as muscle cells, adipocytes, tissues and organs, heart, liver, kidney, and finally, the whole body, which appendages, trunk, the different regions. It's very useful because there's a model at each of these that sums up to, sorry, I got it. Whoop. Uh-oh. It's not up. If you sum each level, you get body weight. And it's very important because if you're making mathematical models for each of these levels, you come up to body weight. But body weight is the composite of all of these different components at each level. And body weight is sort of the paragon for estimating either body fat or muscle mass. Now, when we think of body weight or body mass in an adult, the two major determinants that'll determine your body mass overall is your height. The taller you are, the more you're going to weigh on average, and your level of adiposity. And then there are other covariates in this age, your age and your activity level and so on. But those are the two major things, your height and your level of adiposity. So this is a good example. This is the tallest man in the world and the shortest people in the world. And people have been very interested in how you relate the size, the height of these individuals to their body mass. Very, very old idea. And you can put people into little different cylinders, and you can get their radius and do a lot of mathematical transformations. But Quetelet, in 1842, was really the first to articulate this relationship. And I don't think he was meaning to do it, but he did. He was very interested in body size and shape in people, and there's sociological relationships. But basically, Quetelet said if a man increased equally in all his dimensions, his weight at different ages would be as the cube of his height. And now that's not what he observed. And the cube, because if you increase the volume of a cylinder, it'll increase, if you increase it geometrically, it'll increase its length cube. You can do the math, but basically, but actually what he observed was that it increases the square of height. So mass is proportional to height squared, according to Quetelet. And that's been the subject of a great deal of discussion over the last century. But mathematically, it's basically a power function. How many of you are math-oriented? But in this power function, mass is proportional to height to the k, or k being a power of 2. And you can solve this very simply taking the log and do linear regression analysis. And basically, if you did that, it would look like this. You plot the log of body mass versus the log of height, and the slope of that is the power, and that's where Quetelet got height squared. He found that the slope of that line was 2. And the reason that's important to us today is because if you take mass divided by height squared, it's independent of height. So it's a shape measure, and we can call this BMI, and it's a shape measure that's independent of height. So if you take the tallest person in the world and the shortest person in the world, their mass is going to be different, but mass over height squared should be the same. It's independent of their height. And this is a fundamental concept of BMI, and you can show it very easily. These are just the men in Haynes as an example. I plotted the weight versus their height, and I put a very simple power function in that and get exactly a power of 2. And it's been observed over and over again. There's a lot of little debate around this, but not too much. And this is weight divided by height squared versus height. It's independent of height. Not always perfect, but it's very, very close in most populations. So that's the overall concept of BMI. And Keyes in the 1970s, he showed that weight over height squared was the best measure of adiposity. He plotted percent fat measured by anthropometry and different methods against BMI. He found BMI was the best of these measures. There's ponderal index. There are many other indices, but this was the best one. And you can see the fit is fairly good across a very large population. The R-square is reasonably good. On the other hand, if you take any individual BMI, so I took a BMI of 27 here, you see the range of percent fat is very large. And I've just taken that one BMI unit here, and the BMI ranges from 15 to over 30, almost 40 at one BMI unit. Very large range. And if you just look at who's in the bottom and top of these ranges, you see that older people have a higher percent fat for the same BMI. People who smoke tend to have a little lower body fat for the same BMI. If you're an exerciser, you tend to have a lower body fat for the same BMI. Many of these things you know, but that's the limitation of BMI then. It's good at the population level, but when you get down to individuals, it's not very good. This is just a plot of the power of height versus age when you do that log plot I mentioned before, and you can see the level's about 2, but actually it decreases slightly as you get older, at least in the Haynes data. It drops a little bit below 2. Not much needs to be made about this, but probably that value of 2 is not a physical law of nature. It's an empirical value, and the value of 2 drops off a little bit. So in older people, BMI may not be perfect in terms of the scaling power, and particularly in younger people. This is actually shown by Kedley. When you go to children and adolescents, what you find is the power is 3. It's not 2, and that's why Z-scores are used instead of absolute values for BMI in children, because Z-scores attempt to adjust for this phenomenon. So children are not, can't really be compared across BMI because the power is incorrect. Now, if you take a look at age and relationship to BMI, what you see, and we've heard a lot about this earlier, about how BMI and body composition change with age. But if you match people, same BMI, old and young, and this is values made by DEXA, what you see is a very consistent pattern across men and women. As people get older, at least a cross-sectional sample, they have less of their body mass in their legs and more in their trunk. And there's a little change in the arms, but not very much. So legs get smaller, trunk gets larger as you get older. You have a bigger waist circumference. BMI is the same, height, weight the same. So there's a shift in body mass. And likewise with body composition, there's a loss in muscle as you get older, decrease in fat-free mass, a whole fat-free mass, and increase in fat mass. So as for the same BMI, then they're different in old and young people. There's also a race effect. If you go into Haynes and you use the race categories, race, ethnicity, you have a non-Hispanic white, non-Hispanic black, and Mexican American. Very distinct shape differences. you see relative to white and non-Hispanic whites, you see that blacks tend to have smaller trunks, longer extremities, and longer extremities, smaller trunk, smaller waist circumference. Whoops, I didn't want to do that, did I? Smaller waist circumference, and a little difference in the Mexican Americans in the opposite direction. So same BMI, everything's equal. You see a little smaller percent fat in non-Hispanic blacks, a little higher in Mexican Americans, differences in somatotype, and you can show that non-Hispanic blacks have more muscle, more bone, less body fat for the same BMI. These very old observations. So coming back to this paradigm then of skeletal muscle mass and sarcopenia, if we just think about whole muscle, it can be determined by height, your height. The taller you are, the more muscle you're going to have, your level of adiposity, age, race, genes, and so on, all the way down the line. And mass and composition, as I mentioned earlier, are not directly related, but they're closely related. And I've just shown up here that mass also relates to vascular components and neurological components of the muscle, and that in turn translates to strength, physical strength and performance, and in turn some kind of outcome like a hip fracture with sarcopenia. And that's the paradigm, and adiposity contributes to this overall picture, as I mentioned earlier. So I'd just like to take two of those first things that determine muscle mass, height and adiposity. Well, if you look at how muscle scales to height, they're almost the same as body weight. The power of skeletal muscle and height is about 2.1, bone's about 2.2, slightly higher. Nevertheless, most people normalize skeletal muscle to height squared, as they do for BMI. Very slight difference, probably not clinically relevant, and organs such as the brain scale very differently. Brain scales to height with a power less than 1, and that's because tall and short people have the same size brain. There's not much a difference there, but there's a difference in skeletal dimensions. So muscle scales is height squared. And Gilbert Forbes and John Garrow both very interested in the effects of adiposity on muscle mass. And what they showed is that as people have more adipose tissue, they have more muscle. And that's because of the biomechanical effects of adipose tissue on muscle. If you're carrying around more weight, you have to have more muscle. And these are just some rough estimates. For every kilogram of adipose tissue in women, they get 1/10 of a kilogram more muscle, and men, it's 0.24 kilograms. So if a man has 10 kilograms of adipose tissue, it's going to have 2.4 kilograms of muscle to carry it around. These are rough estimates, but the bottom line being that the amount of adiposity determines, to some extent, the degree of muscularity. Now, if we come back to this idea that there are different levels of body composition, if we take all the way down to the molecular level, we can think of muscle as being water, proteins, glycogen, and other people are going to talk about this later. And also at that level is the DEXA model of muscle, which is that muscle has lean soft tissue and bone mineral and fat. That's the DEXA model of 3 components: lean soft tissue, bone mineral, and fat. And if we come up to the cell level, we have muscle cells, extracellular fluid, and all the way up to the tissue organ level of body composition. So one of the important things, we've heard this earlier, that muscle mass and composition aren't constant. So I'm going to give a few examples of that. And these are just as we go forward in the next few minutes, I'll show you the different technologies for measuring muscle, but beginning with the lowest level in the sense of water and fluids is bioimpedance analysis. DEXA works at the molecular level, creatinine at the cellular level, and these other techniques, anthropometry, ultrasound, CT, and MRI at the whole muscle level. Now, as far as muscle mass and composition, as you lose muscle mass and muscle atrophies, the extracellular fluid compartment increases and the muscle protein component decreases, and you get more collagen in muscle. And this is just protein energy malnutrition, some very old work I did many years ago, but basically the same effects of aging and sarcopenia. Muscle in a sarcopenic muscle will have more connective tissue, more lipid, as we heard earlier, and more collagen. And also we heard about the increase in adiposity of muscle as you get older with muscle atrophy. Here's just the intermuscular adipose tissue. Also, so the anatomic muscle and the actual muscle fibers may differ. The more that adipose tissue you have there, the less connective, less connective tissue you have, and so on. Now, just going on to the techniques in terms of their historical development, anthropometry, Mattiega, 1920s or so, first tried to partition body mass into muscle and non-muscle components, very interesting work, but he used skin fold calipers and a tape measure to do that, and today we can quantify the anthropometric dimensions of the body. And this is just an example, and I know June Stevens will follow me, but basically if you measure multiple circumferences, for example, across the body, those circumferences will relate differently to the components. So, for example, muscle is best quantified by arm and calf circumferences because of anatomic locations of those components. And so you can parse out fat-free mass, but you can also parse out muscle and different adipose tissue components. Now, today we've replaced we're replacing the caliper measurements with digital anthropometry. John's going to speak, John Shepard's going to speak about this a little bit, but basically you get a 3D laser scan, or you get these newer, simpler devices. You stand on it, a little platform, it rotates. You get 400 anthropometric measurements back in less than a minute. You can quantify the entire body shape. You can measure the volumes, the extremities, and you can measure surface area. So that's just now coming online. The earliest, after Mattiega, we developed techniques such as urinary creatinine excretion, Chevroil in the 1800s, and then Berger in the early 1900s. He showed that 1 gram of urine per day, urinary creatinine per day, is equal to 22 kilograms of skeletal muscle. Urinary creatinine urines are hard to collect, so you can show that there's a strong correlation between urinary creatinine and skeletal muscle mass as measured by CT. And now we can use deuterated creatine, measure the creatine pool size. You get a urine, you take a dose, 2 days later or so you get a urine sample, and you can measure the creatine pool size, a very valuable new method. Ultrasound is a very old technique, 1940s. Carl Dusick, first here in Washington, developed some of these technologies. Very old primitive scanners. You could look at an extremity. Today we have extremely powerful devices. We're going to hear more about that from a later speaker. And you can not only get the size of a muscle, but you can get its composition using elastography and echogenicity to look at infiltration with fat and other components. CT, Vicki has given a very nice discussion of CT, and many others have today. First introduced mid-1970s, and with CT you get pixels, and the pixels are defined by Heymsfield units. Unit of 0, as you heard, is water, and if it's below 0, it's fat, and if it's above 0, it's lean. And for a long time, people thought Heymsfield and Heymsfield were the same person, and I had a very high H index, believe me. But they have finally figured out we're not related. And Heymsfield got a Nobel Prize for discovering CT. And basically, you can get the area under these curves. You heard about the complexity of separating fat and lean with CT number. This happens to be fat in the liver, but basically, as muscle becomes more infiltrated with lipid, its Heymsfield unit number goes down, or water. If it gets more water, the Heymsfield unit goes down. So you can quantify the amount of lipid, primarily, hopefully there's not water in there, but lipid in muscle or liver with the Heymsfield unit number. And DEXA, 1980s or so, if you pass an X-ray beam across an element or a tissue, you get absorption of the photons. Those photons, the change in photon energy is different for different energies and each element. So, for example, if you pass 2 energy levels across water, then you will get a differential attenuation net ratio. The 2 energies then can be used to quantify the element. And fat has a lot of hydrogen. Lean tissues have a lot of salt and other elements. And so basically, DEXA works by having a simple X-ray tube. You pass 2 energies across a subject or an element, and you can quantify exactly what it is. Modern DEXA scanner. And the DEXA then 2-dimensional method allows you to quantify the body regions, the mass of each region, and the composition of each region. Region is fat, lean, soft tissue, and bone mineral. And this is, many of you have seen this, is a typical DEXA scan. And if you go to the extremities of the DEXA, you will get the 3 components: fat, lean soft tissue, and bone. And the lean soft tissue is about 50% muscle. And so that component then has been used for appendicular muscle mass. Definitions vary and it's somewhat confusing, but that's the value then that's correlated with total body muscle mass. This just shows total body muscle mass against appendicular lean soft tissue. They are highly correlated. Rick Baumgartner, as you heard, had the smart idea of adjusting that for height squared for the reason as I mentioned earlier. And so appendicular lean mass over height squared, commonly used index. So just in the last minute or two, MRI is a phenomenal technique for measuring body composition, non-radioactive. Also gives you total body muscle mass, and you can quantify intramuscular adipose tissue. You can use spectroscopy to get intramyocellular lipid. And the segmentation, the actual analysis used to be very tedious. Today it's automated. This work by Carlson et al. You send them the image. They give you 20 or 30 muscle groups and total body adipose tissue. You don't have to do it by hand. Lastly, bioimpedance analysis actually can give you very good estimates of muscle mass. If you pass a frequency across tissue, like 50 kilohertz frequency, the drop in impedance across the tissue is related to the amount of water and muscle, water, which is muscle, and fat that's present. And you can buy these commercial devices for measuring regional muscle in the legs and the arms and the trunk. And the advent of DEXA then, if you, this is my last comment, is that if you combine DEXA with BIA, then you can make some very interesting measurements. So this plot shows muscle strength measured by BioDex against leg lean mass. This unpublished work. You get a reasonable relationship between the two. It's not, correlation's not super high. But if you take another phenomenon, that is phase angle measured by bioimpedance, you see across these studies done by Christina Gonzalez that phase angle, which is a measure of muscle quality, decreases in older people. And what you find is if you combine phase angle with the dexaline, you can improve the prediction of strength. You get a significant increase with that prediction. So this is an attempt to get both muscle mass and composition, and you can show that you can improve the prediction of strength. And my last image here, hopefully that will work. I'm not sure if it will. We'll try it. People have made devices like this. Sorry about the noise. Okay. All right, that's enough. Basically, people are building scales with BIA systems in it. You can get muscle mass from the BIA. You can get muscle strength or power from standing up and down, and you get balance. So my last comment then is I think we can build much better technologies for quantifying muscle composition, muscle strength, and performance hopefully will be better predicted from these technologies. Great, thanks very much.
Next up, we have Dr. June Stevens.